Have you ever wondered how your calculator calculates trigonometric functions like sine of x, logarithmic functions like the natural log of x, or even functions like e to the power of x? Well, let me introduce you to Taylor series. In 1715, English mathematician Brooke Taylor discovered a completely new way to represent these functions as never-ending polynomials. But what does that mean exactly? Taylor came up with a way to represent these unique functions as regular polynomials like x squared plus 5x plus 1, or 3x cubed minus x squared plus 2, ones we've been studying, but with an infinite amount of terms instead. Let's say you have a function, sine of x. There exists a polynomial with an infinite amount of terms that perfectly mimics sine of x. The function starts out looking nothing like sine of x, but every time you add another term, starting from x equals 0, the function grows more and more and more similar to sine of x at any point x. And if you continued adding polynomials to the function all the way into infinity, you would have an infinite polynomial, or infinite series, of terms which perfectly mimic sine of x, hence the name Taylor series. Before we start, the standard form for a polynomial is c times x to the 0th power plus c1 times x to the 1st power plus c2 times x to the 2nd plus c3 times x to the 3rd, so on and so forth, if we let c, c1, c2, etc. equal the 1st, 2nd, 3rd, and 4th coefficients of our polynomial respectively. Also, let f of x equal cosine of x and g of x equal our infinite polynomial, or our Taylor series for cosine of x. And for the sake of simplicity, let's start from x equals 0. Now that we have all that out of the way, let's start with the first value. For the function to be even remotely accurate, the function must be in the right place, so g must be equal to f at x equals 0. Therefore, g of 0 must equal 1 because cosine of 0 equals 1. So we set the first coefficient c equal to 1. Now, to mimic our cosine of x as closely as possible at x equals 0, the slope of our Taylor series must also be equal to cosine of x at x equals 0. Therefore, we must take the derivatives of f of x and g of x and equate them so that the slopes of our infinite polynomial, represented by the first coefficient c1, is equal to the slope of cosine x at 0. As we know, the derivative of cosine of x, or cosine prime of x, is negative sine of x. So the derivative of f at 0, or f prime of 0, would be negative sine of 0, which equals 0. On the other side, the derivative of our current Taylor series, 1 plus c1 times x, would be 0 plus c1, according to the power rule. So if we equate the two functions and solve for c1, the first coefficient of our Taylor series would be equal to 1. Now that the value and slope of our Taylor series at x equals 0 are equal to the value and slope of cosine of x at x equals 0, we must make the concavity near 0 of our Taylor series equivalent to the concavity near x equals 0 of cosine of 0 to mirror the function and mimic the original curve as much as possible, like we were doing before. As we've learned, concavity is given by the second derivative of a function. So just like before, we take the second derivative of both functions, f of x, the original function, and g of x, the Taylor series, and equate them to find the second coefficient, c2. The second derivative of cosine of x is negative cosine of x. So at x equals 0, negative cosine of 0 is negative 1. On the other side, we now need to find the second derivative of our Taylor series with the newest term, c2 times x squared added onto it. The second derivative of 1 plus 0 plus c2 times x squared would be 0 plus 0 times 2 times 1 times c2, as per the power rule again. By equating these two and solving for c2, we get c2 equal to negative 1/2. Now, let's do it again, but for the third coefficient, to make our Taylor series even more accurate to cosine of x. The third derivative of cosine of x is sine of x. So if we equate sine of 0, or 0, to the third derivative of our function, with the newest term, c3 times x cubed, added onto it, we get negative 1 equals 0 plus 0 plus 0 plus 3 times 2 times 1 times c3. As you can clearly see, a pattern emerges here. The third, fourth, fifth, sixth, etc. derivatives of our Taylor series must be equal to the third, fourth, fifth, sixth etc. derivatives of our function cosine of x all the way to infinity to make it as accurate to cosine of x as possible. And as we've learned before, the derivatives of cosine of x will loop from cosine of x to negative sine of x to negative cosine of x to sine, and back again. So the derivative of sine of x at 0 will continuously loop from 1 to 0 to negative 1 to 0 again and again. So all we have to do is find the first, second, third, fourth, etc. derivatives of g of x, our Taylor series, going all the way up to infinity, and equate these to our loop of first, second, third, etc. derivatives of cosine of x, 1, 0, negative 1, 0, 1, etc., going all the way up to infinity, to get the remaining coefficients. But how do we find the derivatives of our Taylor series to equate them to the derivative of cosine of x? Well, as you might have noticed, when we take, let's say, the fifth derivative of our Taylor series at x equals 0, every term with a degree higher or lower than 5 turns into 0, because you're either taking the derivative of a constant, which is 0, or you're substituting x for 0, turning the whole term into 0. However, the term with a degree of 5, c5 at times x to the fifth, is equal to 5 times 4 times 3 times 2 times 1 times c5 times x to the 0th power, which is 1. When you take its fifth derivative at x equals 0, it doesn't equate to 0 because there's no x to substitute 0 into, and you aren't taking the derivative of a constant. But the coefficient is 5 times 4 times 3 times 2 times 1 times c5, just because you're applying the power rule and taking the fifth derivative of x to the fifth. This goes for any term in the function too. When we're taking the sixth derivative of our Taylor series, it's equal to 1 times 2 times 3 times 4 times 5 times 6 times c6. When you're taking the fourth, it's equal to 1 times 2 times c3 times 4 times c4. And when you're taking the first, it's equal to 1 times c1. But multiplying 1 times 2 times 3 times 4 times 5, etc., due to the power rule, can be really tedious and annoying, and impossible when you're going all the way up to infinity, which is exactly why mathematicians have come up with factorials. You might have heard that word before, and I'm going to explain how it works right now. A factorial, written as an exclamation point, is just the product of all the positive integers that came before it. If we were to calculate, let's say, factorial 5, or 5 with an exclamation point at the end, it would be equal to 1 times 2 times 3 times 4 times 5. Factorial 6, 7, and 8 being the same thing, with more positive integers multiplied up to the higher values. Factorials come in handy when dealing with Taylor series. So when you see an exclamation point at the end of the number, just know that this is what it means. Now we need to write down the first, second, third, fourth, etc. derivatives of both of our functions at x equals 0 all the way to infinity, equate the two, solve for the coefficients, and substitute the coefficients into our infinite polynomial to get our Taylor series. We already know the derivatives of our original function cosine of x at x equals 0, which is the loop of 1, 0, negative 1, 0, etc. But what are the derivatives of our Taylor series? Well, if we keep writing the derivatives out like we were before, but substitute the numbers at the beginning caused by the power rule with factorials, we get the first derivative equal to 1 factorial times c1, the second equal to 2 factorial times c2, the third 3 factorial times c3, the fourth 4 factorial times c4, so on and so forth. So, if we equate the first, second, third, etc. derivatives of cosine of x, our original function, to the first, second, third, etc. derivatives of our Taylor series, and then solve for the first, second, third, etc. coefficients by dividing the factorial and isolating the coefficients, we're able to calculate the coefficients going all the way to infinity. Remember C, C1, C2, C3 from our Taylor series? All we have to do now is substitute the coefficients we just got into those coefficients in our Taylor series, erase the terms where the coefficient is 0, and boom, there you have it, our Taylor series for cosine of x. And if you look at the graph of cosine of x compared to our Taylor series, you can see how with each new term added to the infinite polynomial, the function grows more and more accurate to cosine of x starting from x equals 0. But how do we actually write this function as an infinite sum? Well, there exists a way to write it using the summation notation. I don't have time to go over it right now, but it's basically just a generalized version of our Taylor series. You can try it out right now though. Take the big fraction on the right and substitute any positive integer like 3, 7, or 55 into k, and it will spit out the third, seventh, or 55th term in our Taylor series for cosine of x. But Taylor series are just the beginning. They're an incredibly useful facet of calculus that can open your mind to thousands of possibilities, being able to represent complex functions as simple polynomials.